Hello everyone. Today I am presenting our EGU2021 contribution. It's some kind of tutorial based on our paper Uncertainty Estimation with Deep Learning for Rainfall-runoff Modeling, which I wrote with Frederik, Kratzert, Gauch, Alden, Sampson, Johannes, Brandstetter, Günter, Klambauer, Sepp, Hochreiter and greeneering. And the idea of this presentation here is to give a high-level overview, like show the concept, give you an intuition about it, and not go too much into technicalities. It's more hand-wavy ideas. I will just start. So here is the motivation. Normally, if we consider a single time step and we simulate it, we think about it like this. We have a point observation and we have 1 point of simulation. And because a point would be a quite exact prediction, we use uncertainty quantification techniques such as an error model or Monte Carlo Markov chain sampling, some formal Bayesian method, or whatever we do to provide a distribution or an interval around it to get a notion of the uncertainty of the simulation or of the potential error that we will make. Now with data-driven methods, we can do this differently. We can directly estimate the distribution as an estimation. And then if we need it, we can still derive the point estimates from it or an interval estimate from the distribution because we already have a very rich representation of the actual prediction. Ultimately, these two should converge. So if you have very good methods for estimating this distribution because we can only provide an estimate, or if we have very good methods for estimating the uncertainty around it, those should come to the same conclusion. But for machine learning models or for data-driven models, it's often more natural and more nice to go directly to the distribution. So what should come out should look somehow like this. We have a time series of observations. This would be our streamflow observations, for example. And instead of having a second point time series with just points in time, we have a distribution over each point that we observe, or that we can observe. So this will be our predictions, the simulations. Now, the ideas draw from a lot of sources, but I would especially like to mention 3 of them, which I will come back to them later. One is the one from Bishop, who introduced mixture density networks. One is the one from Brandau, who pushed them forward into a quite nice idea. And lastly from Kratzert et al., which is our universal model where we use an LSTM for rainfall runoff prediction, and which is trained over 600 basins on the continental USA, and is a single model that works for all of them, and it also works quite nicely out of distribution. So for now, let's assume that those are Gaussian distribution, which is of course a very special case, but you will relax it later. It's just to give it the right intuition. So the first thing that we have to find out for the data-driven method is how can we define a loss for those Gaussians? And probably most of you know it, but it's nice as a repetition. So if you have a Gaussian density and the cumulative distribution, the corresponding cumulative distribution function, then the probability is an integral on the density or a point on the cumulative, because the cumulative is nothing else than the integral of the density. Vice versa, if you think of the likelihood, we have a point in the density function, and if we go to the distribution, the cumulative distribution function, it's a derivative, well, which kind of makes sense. And now that means that we can use the likelihood as a loss, or the negative likelihood if you want to minimize, because it's a loss. So the way to think about this, the Gaussian has 2 parameters, the mean and the sigma, the mean and the variance or the standard deviation. Depends on what you want to plug in here. And to maximize the likelihood, we would move the mu and reduce the sigma, and then we get a higher likelihood, which means that we can plug it in as an objective function to optimize. Of course, that in itself would be useless. So what would happen, for example, here, for each point we would have to estimate 2 parameters, And what will happen is that the sigma will converge to 0 and the mu to the point. So now we have two numbers which are used, where one is over 0 to represent the points. So what we actually want to have is a prediction model or a predictive model which gives us a conditional. So that's drawn here roughly, or a sketch of it. Let's say we have a set of inputs, like the meteorological inputs that we always use for each time step, say precipitation and temperature. And then we have a rich prediction model which gives us the sigma and the mu as a function of the input. This way we can go over the time and then describe how the sigma and the mu evolve. Now I wrote here MPR because that's quite a parallel which might some of you know, or a way to think about it which you are familiar with. So MPR has this transfer function which have global parameters, and those map to the parameters of the model which are local. So we have one set of global parameters which map local parameters, and the model adapts at each point in space. This, for thinking, this can be seen very similar. We have the predictive model would have the global parameters which are trained or calibrated once, and then it gives us a sigma and a mu which then changes over time, for example. But of course the Gaussian has its limits. So one thing that we saw quite early are for small basins, or for if you have very low runoffs, then the Gaussian is a bit problematic because of its symmetry property. And once you go towards 0, you have to have again like a delta spike, or you have to move the mean a bit up so that you overestimate, or you have to live with probabilities that are on a negative runoff space. So quite problematic. But even for high runoff, often we don't expect a symmetrical distribution. We expect that our mean should be quite near to what we want to have, but then we have a higher, the mass above it is more spread out than the mass below it. It's not symmetrical around the mean. So we need something richer to describe in actuality what's going on. This is where the publication of Bishop comes in. So what Bishop proposes is to use not Gaussians, but Gaussians are just the components, or the densities are just the components, and we can mix them together. So we still plug in the X to our prediction model, which he proposes a neural network, and which we also think is quite nice. But then you have these additional parameters in addition to the density parameters, which are the weights. The weights obey the following rule: all weights sum to 1, and each weight has to be bigger than 0. So you can think of the weights as probabilities in themselves. And if you have the Gaussian, then we have two additional parameters. So here I wrote down an example of two mixtures, but you can have more. It would be like the first weight times the first Gaussian and the second weight times the second Gaussian. Quite easy. Here is an illustration of this. Let's say the first weight is smaller than the second weight. Then and the gray ones are the two Gaussians. Then you can see the new orange one. You can trace it out. It's lower here and higher here. It's drawn a bit wrongly, but you get the idea. And you can already see that this has the property to consider asymmetric distributions now. And if we mix more of the Gaussians, we can have multimodal distributions and all kind of different, you can approximate all kind of different distributions here. Now what we saw is that this directly maps to our setting of 2019, where we introduced a universal model, which used an LSTM as the neural network. And the LSTM is very nice for simulation models because it has also internal states that evolve with time, which parallel the internal states if we want of conceptual models that we use in hydrology all the time. The setup is roughly this, that we provide two kinds of inputs: the dynamical inputs, which are the meteorological inputs that I described first, but also static inputs, which basically are things that describe the location in which we are in, and then modulate the dynamic accordingly within the network. So these are things like the percentage of sand or clay in the soil or the land use class. And while previously we had made point predictions, we now use the concept of Bishop to derive those densities or these conditional probabilities. So this is quite nice. Let me also shortly say the idea of Brandstetter. Brandstetter then had two big ideas. One is that he used a sampling-based method, which introduces a new parameter, but then we don't have to estimate the weights anymore. And then the network learns an implicit representation of the uncertainty. Here the second one, which I will shortly describe. I would just shortly say nice properties of those. So in the LSTM that we previously used, we already saw that the LSTM internally learns representations that are useful for making prediction. For example, if it's important to track a reservoir, like let's say there's no accumulation and depletion, then it will internally learn a representation of that. And here it's the same. So it will internally learn uncertainty-based representation if it has to predict the distribution in the first place. So this is another reason why it's very nice to focus on the distribution directly, not indirectly, because then you have internal representation that evolve over time, which map to the distribution itself. Okay, the second thing which enabled this whole idea of Brandstetter was that he introduced a different component than the Gaussian. So he used asymmetric Laplacian distributions. And the Laplacian distribution is very nice in the first place because it basically, the way it tells how the distribution should behave is that we should make a lot of small divergences and then sometimes big ones, which is, in my opinion, exactly what I observed with the LSTM, but also with conventional hydrological models. So I think it's within the data, the distribution is already something like that. It also is a natural border to the heavy-tailed distributions, and so which we wouldn't want to leave. So this is exactly at the border, which is also nice. And the asymmetry, so it has an asymmetry parameter where it weights the two exponentials, connects it to this problem that I described before, where we have the low ones, where we can move the mass from one set of the distribution to the others. And as a matter of fact, we tried all three approaches. So the implicit one from Brandstetter, just replacing the normals with asymmetric Laplacians, and the one from Bishop, where we use the simple one from Bishop, where we use the normal distributions. And the best one was just 3 components of asymmetric Laplacian. It was the best one that we found. It can be, of course, different, and we had always considered a simulation setting, so it could also be if you have a forecast setting that you have to adapt the architecture a little bit. But in general, everything can also be applied to forecast settings or to other settings. It's a very general concept. Okay, and with this I end. I hope to see you all next year. Thank you very much.